A chunk of ice and rock from another star system is cutting across the solar system right now. Above city lights and cloud cover, beyond the satellites and space junk, something alien in origin is gliding through the sun's gravity field, then leaving forever. Most people never hear its name. Astronomers call it Three-Eye Atlas. To them, it is a once-in-a-generation kind of visitor. Only the third confirmed object ever seen that comes from interstellar space, and the first one that clearly behaves like a classic comet with a fuzzy coma and a streaming tail. This is not a doomsday rock and not a secret impact scenario. It is something more subtle and more interesting. It is a physical sample from another solar system, drifting past within range of our telescopes, carrying chemical fingerprints of a place the human species will never reach. In this video, the focus stays on that line between what is known and what is guessed, the facts of Three-Eye Atlas, and the theories built on top of those facts. The official designation says a lot in a small code. The number 3 means it is the third interstellar object ever cataloged, after One-Eye Oumuamua in 2017 and Two-Eye Borisov in 2019. The I stands for interstellar. Atlas is the survey that found it, the Asteroid Terrestrial Impact Last Alert System, using a remotely operated telescope in Chile. It was first spotted on the 1st of July 2025. From those first images, astronomers measured its motion against the background stars. They reconstructed an orbit that does not loop around the sun in a closed ellipse. Instead, it is sharply open, hyperbolic, the classic signature of an object just passing through. When Three-Eye Atlas was first detected, it was already inside the orbit of Jupiter and moving at roughly 60 kilometers per second relative to the sun, over 130,000 miles per hour. As it fell toward the sun, gravity accelerated it further, up to around 150,000 miles per hour at its closest approach in late October 2025. Then, as it moved away, the sun's pull began to slow it again, but not enough to capture it. The numbers matter. At every point along the path, even after subtracting the pull of the sun, the object keeps a leftover speed, a hyperbolic excess that no planet in our system could have given it. It is moving too fast, on too open a trajectory, to have been thrown out by Jupiter or any other planet. The only conclusion that fits the physics is that Atlas was already moving that fast before it ever entered our neighborhood. It was born elsewhere. For Earth, the story is calm. The comet never comes closer than about 1.8 astronomical units from our planet, almost twice the distance between Earth and the Sun. That closest approach happens on the 19th of December 2025, and for us, it is a safe, distant flyby that only matters to telescopes and observatories. The orbit gives something else, though. When astronomers run the path backwards, they can see which direction in the sky this object came from before the sun deflected it. That direction is not random. Tracing the trajectory back in time points to the constellation Sagittarius, near the thick band of the Milky Way's center. The object approached from the southern sky, from roughly the opposite direction of the sun's own motion through the local stars. That detail matters, because many models once suggested that interstellar debris should arrive preferentially from the solar apex, the direction the sun is moving toward. Atlas does the opposite. It slides in from the south, retrograde with respect to the planetary orbits, and tilted only a few degrees from the ecliptic plane. That combination makes it both surprising and, in a way, convenient, because its path passes right through the region of sky our telescopes already monitor heavily. Here, the line between fact and theory appears. The orbit is measured, the speed is measured, the incoming direction is measured. What these things say about its birthplace is still a matter of models.
One view pictures Atlas as a small survivor from a crowded inner regions of another galaxy of planets and dust around a star near the galactic center. Over billions of years, gravitational encounters between giant planets and icy leftovers can fling many such objects out into interstellar space. In that story, this comet spent unthinkable stretches of time in the dark between the stars before wandering near the sun by chance. Another view is more cautious. The Milky Way is full of old systems, and tracing a single object back to a specific population is almost impossible. Local gravitational tugs, passing stars, and the galaxy's own potential warp the path over millions of years. So for now, astronomers talk less about a specific home star and more about a broad statistical truth. Interstellar space is not empty. It is seeded with countless fragments like this, and our telescopes are only just sensitive enough to begin noticing a few of them. To move beyond broad guesses, they need more than an orbit. They need to know what this thing is made of. Even in large telescopes, Atlas never appears as a sharp point. It looks like a soft, fuzzy glow with a condensed core and a faint tail stretching away. That glow is the coma, a cloud of gas and dust released as sunlight heats the object's surface. Inside that coma, almost completely hidden, sits a solid nucleus made of ice, rock, and complex frozen molecules. Because the coma overshines the nucleus, the exact size of the solid body is hard to pin down. From the brightness and allowing for how reflective the dust might be, astronomers estimate a range from a few hundred meters up to a few kilometers across. JWST data and other observations push the most likely size toward the lower end, probably less than a kilometer in diameter. For something crossing the entire solar system, it's surprisingly small. Spectra tell a deeper story. When instruments split the light from the coma into its component colors, clear signatures appear. Strong bands of carbon dioxide gas, along with water vapor, traces of water ice, carbon monoxide, and other minor gases. The coma of Atlas seems especially rich in CO2, compared with what astronomers often see in many comets from our own Oort cloud. That is still observation. The theoretical step begins when scientists try to connect those molecules to a physical place. A CO2-rich mixture can point to formation in a very cold region of a protoplanetary disk far from its host star, where CO2 ice is stable, but where some of the more volatile ices have already been partially lost or processed. It can also reflect local chemistry in the cloud of gas and dust that formed that system in the first place. Another detail sits underneath. Instruments sensitive enough can detect isotopes, slightly heavier versions of atoms. There are hints of carbon-13 in Atlas, the less common isotope of carbon. The exact ratios are still being refined, but they matter. If future measurements show a clear difference between this comet's isotopic mix and typical solar system comets, then Atlas becomes a chemical fingerprint from a different cosmic neighborhood, not just a random snowball. So far, nothing in the composition requires exotic explanations. It behaves like an active comet heated by the sun, outgassing volatile ices and dragging dust into a tail. The interesting tension comes from the way that activity is organized.
Debate over anomalies.
Astrophotographers and professional observatories alike have captured striking images of Atlas. Some show multiple narrow jets streaming away from the nucleus. One image combines many long exposures and reveals an anti-tail pointing toward the sun and a longer, tightly collimated tail stretching away. From different angles, the structure almost looks like a spray of fountain jets frozen in space. In mainstream comet science, this is still natural behavior. The sun heats patches of surface ice, gas vents out from those active spots, and dust rides along, forming jets. As the nucleus rotates, those jets sweep through space like slowly moving searchlights, carving spiral or fan shapes in the coma. Radiation pressure from sunlight then pushes smaller particles backward, creating the familiar tail. Variations in jet strength, rotation rate, and viewing geometry can generate complex patterns, including anti-tails and multiple separate streams. NASA and ESA teams have combined images from several spacecraft and telescopes to cross-check these interpretations. Their conclusion, presented in recent briefings and fact sheets, is straightforward. Every measurement of Atlas so far fits within the range of behavior expected from a highly active comet on a hyperbolic orbit. That is why official communications describe it unambiguously as an interstellar comet, not a mysterious unknown object. On the other side of the discussion, a more speculative line of thought exists. Astrophysicist aviloeb and collaborators have argued that some aspects of Atlas are worth examining under a different lens. They point to the alignment of the orbit with the planetary plane, the structure of the jets, and some early interpretations of its apparent brightness and mass. In that framing, the series of narrow jets could in principle be compared to thrusters firing on a spacecraft rather than simple gas vents. This is where a clear boundary between science and speculation is important. The data themselves are real: images, spectra, trajectories. The claim that thrusters exist on the surface is not supported by direct evidence. No regular timing pattern from controlled burns, no non-gravitational acceleration clearly outside the range of comet outgassing, no sharp edges or artificial shapes resolved in the images. Many astronomers have publicly criticized the statistical and physical arguments behind the spacecraft interpretation, seeing them as an overreach beyond what the observations justify. Still, this tension plays a role in the story. Interstellar objects are rare, and human imagination reacts strongly to them. One side leans on the principle that extraordinary claims need extraordinary evidence. The other side pushes to keep the door open to unconventional possibilities. For Atlas, the weight of current evidence rests firmly on the side of a natural object. Underneath that debate lies a quieter and perhaps more important question. Natural or not, what does this comet tell us about how common interstellar debris really is, and about how planetary systems form and evolve across the galaxy? Think of Atlas as a fossil shard chipped from the early history of another solar system. In our own system, comets are leftovers from the building of the planets. Far out in the Kuiper Belt and the Oort cloud, trillions of icy bodies orbit in the dark. Occasionally, gravity nudges one inward. The sun warms it, a tail forms, and for a short time, the inner planets see a visitor from the system's own outer storage. Interstellar comets, like Atlas, extend this idea to the entire galaxy. At some point in its past, this body orbited another star. Gravitational encounters, probably with giant planets, eventually slingshotted it hard enough to escape. Once that happened, it drifted through space for ages, carrying with it a snapshot of its birth environment in its ice, dust, and isotopes. Now imagine billions of other systems doing the same thing. They all eject debris. Some of that debris eventually crosses the paths of neighboring stars. Suddenly, the Milky Way looks less like a set of isolated bubbles and more like a slow, constant exchange of material between distant planetary systems. The three known interstellar visitors each fit this picture in a different way. Oumuamua, with its strange light curve and lack of clear coma, pushed some researchers to explore ideas like fractal ice or thin, pancake-shaped fragments, and even light sails in the extreme versions. Borisov looked more like a conventional long-period comet, with a clear coma and tail, and its composition fit well within what is seen in many solar system comets. Atlas sits somewhere in between. It behaves like a comet, but its CO2-heavy coma and some aspects of its trajectory add new data points to the small but growing library of interstellar ice. From a planetary science point of view, this matters more than the headline debate about alien technology. If enough objects like Atlas are detected and characterized, scientists can start to compare their chemistry statistically with that of our own comets. That comparison can reveal whether the building blocks of planets are similar across many systems or whether our solar system is chemically unusual. Even the simple count of detected interstellar objects feeds back into models. If only 3 have been seen in less than a decade with the current generation of surveys, it suggests a certain minimum density of debris per cubic light year in the local region of the galaxy. Future surveys, like the Vera Rubin Observatory's Legacy Survey of Space and Time, will push that sensitivity even further, and almost certainly add more visitors to the list. Each new object tightens the constraints and turns vague estimates into solid numbers.
What comes next?
For now, Atlas continues its passage. After its close pass by Mars in early October and its perihelion near the end of that month, it crossed the inner solar system plane and headed outward again. It passes far from Earth in December, then continues toward a distant encounter with Jupiter's orbit in March 2026, after which the Sun's influence fades. Professional observatories will keep following it as long as they can. Spacecraft around Mars, solar observatories, and large ground-based telescopes already collected a library of images and spectra at different wavelengths, from visible light through infrared and ultraviolet. Some of these images look underwhelming at first glance, just fuzzy blobs, but the real information hides in the precise brightness patterns and in the detailed spectra. Amateur astronomers with good telescopes and dark skies have a chance to see it as a faint smudge and perhaps record their own contributions to the global dataset. Websites that track comet visibility show its changing position night by night, turning this rare event into something an individual observer can actually chase. Beyond this specific comet, space agencies are already planning for a future where such visitors are expected, not surprising. ESA's Comet Interceptor mission, scheduled for launch later in the decade, will park a spacecraft near the Sun-Earth L2 point, waiting in a standby orbit. When a suitable pristine comet is discovered passing through the inner solar system, Comet Interceptor will fire its engines and race out for a close flyby, releasing small probes to image and sample the target's environment from different angles. The mission is primarily designed for long-period comets from our own Oort cloud, but its architecture could, in principle, also be used on the right kind of interstellar object. In parallel, scientists on both sides of the facts versus theories line will continue to publish papers. Dynamic specialists refine the orbit and search for any subtle non-gravitational forces caused by outgassing. Spectroscopists wrestle with noisy data to extract more precise abundances for each molecule and isotope in the coma. More speculative thinkers test models where interstellar comets might sometimes be artificial objects among many natural ones, and they look for clear observational signatures that could distinguish these cases in a future sample. All of this happens while, far above, the comet itself simply moves on. It does not care about labels, debates, or mission proposals. Once it passes Jupiter, the Sun becomes just another bright star behind it. So, in the background of normal life, behind screens and deadlines, a small, dark nucleus wrapped in gas and dust sweeps through the solar system. It came from another sun, shaped by different planets, different collisions, different histories. It leaves almost no trace behind, just data points in archives, and a subtle shift in how scientists think about the galaxy. The facts say that Atlas is a natural comet on a hyperbolic orbit, rich in carbon dioxide, moving too fast to ever return. The theories use those facts as a foundation to talk about planet formation, interstellar debris, and, at the fringes, possibilities of technology. In the end, the strongest part of the story is not a dramatic twist, but a quiet realization. Interstellar space is not a clean vacuum. It is full of these wandering pieces of frozen history.
Right now, one of them is here, paying a single visit to our sun before it vanishes into the dark again. If that idea stays in mind the next time the night sky is visible, that faint, almost invisible visitor above becomes more than a blur. It becomes a reminder that even distant solar systems leave footprints, and sometimes those footprints pass right above our heads.